Good evening, ladies and gentlemen. How are you all doing this evening? I'm also well, thank you, guys. So, according to our schedule, our semester test is not far away. Yes, the semester test is next week, the 9th of June. So, just be prepared for it. So, I will give more details about the semester tests uh, tomorrow evening. No, it's not on campus. It will be an online test. So for the test, I plan for we're going to try for everyone to be logged into um, Blackboard Collaborate, and then I will give you your time to do your test in. So if there's problems or anything, then you can just unmute yourself or type, and I can try to the best of my abilities to help you guys. Uh, so the online test will be multiple choice. The test will be on ClickUp, but if you guys can be on Blackboard Collaborate, that will really help. It's a pleasure. So I'm just going to give you guys the announcement. Posted the announcement on ClickUp a while back. So where is the group? I posted on the group as well. So I can't find the chat, but let me quickly go to Blackboard Collaborate. Go to announcements. So the semester test next week will be from 5:30 the afternoon to 8 o'clock. So you will have 2.5 hours to complete the test. Now your webcam's is not going to be on, but you have to be logged into Blackboard Collaborate to so I can help you if there's a problem. So let me check. I still have to. It's going to be a closed book test. So I'm going to upload that just after the lectures tonight. So where is that now? I want to give you more information. I still have to create a few more questions for the test. So it's going to be 50 questions, 2.5 hours. Yes, 50, but remember it's multiple choice. All questions will be multiple choice. No, you won't get a formula sheet. 50, 50. So each question will have 5 options. Yes, backtracking will be allowed. And if it will help you guys, I did it last year as well. I will, before this weekend, so let's see, the 9th is next week, Wednesday. So by this Wednesday, I will provide you guys with a mock semester test that will have 20 questions for you to get a feel on what exam will be like and what type of questions can be expected. And then on next week, Tuesday's class, we will go through the answers of the mock test, if that is fine with you guys. Pleasure, guys. So how's your other modules going so far? Why? What happened? What is so difficult? So I see a lot of people complaining about COS 151. So how hard is the test comparison to the quiz? The test is going to be a little bit more difficult than the quiz, but almost on the same standard. Oh, so that's assembly language, COS 151. I remember when I did assembly, that is a horrible programming language. What's the weighting of the semester test? The semester test will count 50% of your semester mark. Then your assignment will count 40%, and your quizzes 10%. So before we begin with tonight's lecture, do you guys have any questions about the previous work that we covered? Okay, so explain what degenerate matter is. Okay, so let me get the whiteboard. So remember, in all the matter we have, the easiest example is there are different valence orbits where electrons can sit. So let's make it this way. For energy levels and where it can be. So when we have electrons, the electrons will sit on the lower valence orbits, And when you go to a higher valence orbit, more energy is needed to go to a higher valence orbit. So then we can put another electron there, and more energy is needed to go even to a more higher level. And more energy is needed to go to a even more high level. But degenerate matter, such as the core of stars, we have the pressure temperature thermostat that controls the equilibrium of a star. So the outgoing force must counter the gravity from the layers above. But what happens in the core is, because of the pressure and temperature, it becomes more compressed, and all the electrons fills up these low orbits. So more energy is needed to go to the higher orbits. But in degenerate matter, due to the pressure and temperature, energy has been added to the material that all Vibelins orbits is now full. So it means that the material cannot add more electrons to it. And because it's full of electrons, it cannot be compressed any further. And that is why it's called degenerate matter, because the matter cannot be compressed any further and all its electron spaces is already filled. Does that answer your question? So I'm quickly looking, and it looks like, with pleasure, with class attendance, we have the usual group tonight, and thank you for that, guys. So for tonight's lecture, we're going to continue our discussion on neutron star and black holes. I saw made a little typo in the slides. It's not black holes, it's black holes. We have discussed about the evolution of stars in a previous lecture, but now we can discuss what actually is neutron stars, black holes, and compact objects that has disks and jets with electromagnetic radiation streaming out of them. So we already saw this graph where we can see from a stellar nebula we can have average star size, red giant, planetary nebula, or white dwarf. Now, nebula, star, super red giant, supernova, and then a neutron star or black hole. Last year we ended off with white dwarfs and supernova. But now we're going to delve a little bit deeper into neutron stars and black holes. In the last 2 years, you have traced the story of stars from birth to death. By now, you may be asking a simple question: what's left? The answer depends on the mass of a star. You already know that stars, like the Sun, produce white dwarf corpses. But more massive stars leave behind the strangest beasts in this cosmic zoo. Now you are ready to meet neutron stars and black holes, and you will explore, and your exploration will answer these 4 fundamental questions. So firstly, we're going to look at: how does theory predict the existence of neutron stars? How do astronomers know neutron stars really exist? How does theory predict the existence of black holes? And how can astronomers know that black holes really exist? So by determining how to study neutron stars, and black holes. Everything come down to our opening lecture at the beginning of the semester on what's happening in nature and what does the mathematical model tells us about what we're going to observe. Speaking about this, a bit off topic. Do you guys perhaps know why it is so difficult to predict the weather?
So I have
Yes, Mr. Luguio.
so is it not because like for example, so there's too many particles that could affect the weather. It's like so just like for example, like one particle not being in a certain position could affect the whole system. That is my take.
Yes, you are correct. And looking in the comments, it is too many variables to consider. And that's exactly the term I'm looking for, the butterfly effect. So bingo, well done. So what's so difficult to predict the weather is there's too many variables that can change. And it all comes down to the butterfly effect. So in one area, a small variable can change. But in another area, that can have a huge effect. So now a comment, the amount of time to predict the weather is too much. So no, so that's a small changes can produce big results. So currently the furthest we can predict weather away, so in speaking of a time scale, where we can get fairly all right results is a week away. But further than a week away, then our mathematical model starts to break down. So the best to predict the weather is 2 days, 1 day ahead. And it doesn't matter how powerful your supercomputer is, you need to account for all the variables and you need to constantly change the variables to get accurate readings. So now, and previously I've dealt with some people saying, yeah, the weathermen on TV and people, meteorologists, are useless predicting the weather. No, they're not useless predicting the weather. It's just difficult to predict the weather. And global warming has made it a lot harder because due to global warming, there's more fluctuations in our climate zones, and that can cause weather to change faster than predicted. And if you need a system that can accurately predict the weather, think about it. So what system do we have that produces the weather? So that means Earth as a whole creates weather systems. So if we need a mathematical model that can predict the weather systems, we need a model that is as complicated as Earth itself to predict the weather. So with neutron stars and black holes, gravity also always wins. No matter how long a star struggles to withstand its own gravity, it must eventually exhaust its fields and die by collapsing. These stars that do not destroy themselves in the process become one of three types of compact objects: white dwarfs, neutron stars, or black holes. A neutron star containing a little over one solar mass, compressed to a radius of about 10 kilometers, can be produced by a type 2 supernova. For comparison, a white dwarf has about the same mass, but is about the size of Earth. A neutron star's density is so high that physicists calculated this material is stable only as a fluid of neutrons. Theory predicts that such an object would spin a number of times a second, be nearly as hot as the surface of the inside of the sun, and have a magnetic field a trillion times stronger than Earth's. Two questions occur to you immediately. Firstly, how could any theory predict such a bizarre object? And secondly, do neutron stars really exist? And can you guys, what is your guys' opinion about it? How can theory predict such an object? Yes, it's exactly the math, but how do you formulate a math? How do you get to the theory? What makes you think and say, okay, let's see, there should be a neutron star because something happens? Yes, mathematical models. So we can come up with these theories by observing different stars. So yes, Albert Einstein, this is a bit before Albert Einstein, but yes, Mr. Visagie, it's observation. So we already observe stars. We observe stars at the end of their life cycle. And then we know about the conservation of matter. So then we can start theorizing of what might happen. So neutrons were discovered in a laboratory in February 1932. Only 2 years later, in January 1934, Caltech astronomers Walter Baade and Fritz Zwicky published a seminal paper. They showed that some novae in historical records were much more luminous than the rest and suggested that these were caused by the collapse of a massive star's core, resulting in an explosion they named supernova. The core of the star they proposed would form a small and tremendously dense sphere of neutrons, and Zwicky coined the term neutron star. So a bit off topic, but Caltech does amazing work. You guys all familiar with Caltech? California, there's a university, the California Institute of Technology. So Caltech is situated in Pasadena, California. So NASA's Jet Propulsion Laboratory also operates out of Caltech. Caltech is probably the most difficult university to get into. So yes, many Nobel laureates are from there. So how many students do you think UP has? Yes, UP has about 60,000 students registered, and that is from first year to PhD students. Caltech only has 6,000 students. So yes, so Caltech has 4,000 undergrads and 2,000 postgrads. MIT is also very difficult to get in, but it's much more difficult getting into Caltech than MIT. So Caltech is but why is it so difficult? Because Caltech only wants to take in the best of the best of the best. Harvard is not overhyped. Harvard is a very good university, but it all depends on what you want to do at the university. So, for example, Caltech specializes in two fields, and that is engineering and physics. It has not all the faculties and departments other universities have. It has a few other departments as well, but Caltech primarily does engineering and physics. So that's why it's important. That's why it's so difficult. Caltech also does a lot of research, and because NASA uses Caltech for the Jet Propulsion Laboratory, there's a lot of work coming out of Caltech. So over the following years, scientists applied the principles of quantum mechanics to see if such an object was indeed possible. Neutrons spin in much the way that electrons do, which means that neutrons must obey the Pauli exclusion principle. In other words, if neutrons are packed together tightly enough, they can become degenerate just as electrons do. White dwarfs are supported by degenerate electrons, and quantum mechanics predicts that an even denser mass of neutrons could support itself by the pressure of degenerate neutrons. So question, sir, do you think the type of education you receive can hinder your development as a scientist, even though the content that is learned is the same? No, so the important thing with your education is it doesn't matter which university you attend, the work you will be learning is exactly the same. So if you do a first year physics course at UP, UJ, WITS, UCT, INISA, Northwest University, the course will exactly be the same. The only thing where stuff starts differing is when you do a postgraduate degree, such as master's or PhD, because there, certain universities doesn't provide the same research, doesn't provide the same programs, but because it all depends on what the research is being done by the different institutes. So say, for example, what is a great example I can give you? Great example. If you want to do research in lasers, then UJ is a great university for it because they have a fantastic laser research group. But looking at other universities, they don't have laser research groups. So if you want to study lasers, then UJ is the correct place to do that. For example, want to do particle physics and quantum mechanics, then a great university for that is UP or WITS, because UP and WITS both have particle accelerators on campus. So it all depends on what you want to do. So undergrad, everything is basically the same, but postgrad, you need to go to where the research is you are interested in. So question one said that there's something something called singularity in math. Does that singularity means the singularity that we know in physics? Yes, that's exactly it. That's the point. So usually to make it easier, a black hole is a singularity, but we will come to that now. How does the core of a collapsing star become a mass of neutrons? Nuclear physics provide an explanation. As it begins, the core collapses inward. If a collapsing core, someone was unmuted. So is that how to predict black holes and such? Yes, we will discuss that now as well. Nuclear physics provides an explanation. As the supernova begins, the core collapses inward. If the collapsing core is more massive than a Chandrasekhar limit of 1.4 solar masses, then it cannot reach stability as a white dwarf because the weight is too great to be supported by degenerate electrons. The collapse of the core continues, and atomic nuclei are broken apart by gamma rays. Almost instantly, the increasing density forces the free protons to combine with electrons and become neutrons by this reaction. So we're going to look at it now. So this is the reaction to theoretical prediction of neutron stars. So it's a result production of each neutron. So N is a neutrino NU, or N mu rather. You learned in a previous chapter that a burst of neutrinos during a supernova explosion helps blast the envelope of a star. The star's core is left behind as a neutron star, so you don't need to know this equation at all. It's just something interesting I thought I'd put into the slides to show the equation to predict a neutron star. So, looking at our nice classification, which stars do you think produce neutron stars? Definitely a O. A to O is correct, but you can add F to it as well. So remember, a G-type star is the same as our own sun. Yes, Mr. Lebuya.
So do stars have distinct sizes? Like, for example, we spoke about atoms having energy, having specific energy levels. Would that be the same with the sizes of stars?
Yes, and when you plot that, then you get the HR diagram.
So it's not necessarily only about temperature, it's also the size.
Yes, so you see temperature and pressure determines the size.
Oh, okay. Thank you, sir.
It's a pleasure. So yes, in this image, we will have it from G to O. So as you learned in the previous chapters, a star that begins its life with less than about 8 solar masses can lose enough mass to die by forming a planetary nebula and then leaving behind a white dwarf. More massive stars also lose mass rapidly, but model calculations indicate they cannot shed mass fast enough to reduce their mass below the Chandrasekhar limit. So it seems likely that they must die in supernova explosions. Theoretical calculations suggest that stars that begin life on the main sequence with roughly 8 to 20 solar masses will leave behind a neutron star. Stars even more massive than that are thought to form black holes. But how massive can a neutron star be? That is a critical question and a difficult one to answer because scientists don't know the strength of pure neutron material. They can't make such matter in a laboratory. So its properties must be predicted theoretically. The most widely accepted calculations suggest that a neutron star cannot be more massive than about 3 solar masses. If a neutron star were more massive than that, the degenerate neutrons would not be able to support the weight, and the object would collapse, presumably becoming a black hole. Two of the most massive neutron stars observed have masses of 1.94 and 2.74 solar masses, evidence in favor of the hypothesis. So how big are neutron stars? Mathematical models predict that a neutron star should only be 10 or so kilometers in radius, which combined with a typical mass means it must have a density of about 10 to the power 15 grams per cubic centimeter. This is roughly the density of an atomic nucleus. So you can think of a neutron star as matter with absolutely all the empty space squeezed out of it. On Earth, a sugar cube-sized lump of this material would weigh more than 1 billion tons, which is mind-boggling. So here's just a representation. A tennis ball in the roadmap illustrates the scale of a neutron star. Such an object containing slightly more mass than the Sun would fit with room to spare inside the beltway around Washington, D.C. Simple physics, the same physics you have used in previous chapters to understand normal stars, predicts that neutron stars should be hot, spin rapidly, and have strong magnetic fields. You have seen that contraction heats the gas in a star. As gas particles fall inward, they pick up speed, and when they collide, their speeds become thermal energy. The sudden collapse of the core of a massive star to a radius of 10 kilometers should heat it to 1,000,000,000 degrees. Astronomers calculate that neutron stars should initially cool rapidly from that astonishingly high temperature because neutrinos can escape from the entire volume and carry energy away. After a few years, neutron stars will cool down to a mere million degrees or so, and neutrinos won't be produced in bulk. From that point on, neutron stars should cool slowly because the heat can escape only from the surface, and neutron stars are so small they have little surface from which to radiate. The principle of conservation of angular momentum. So this is a principle that will pop up in physics quite a lot. Predicts that neutron stars should spin rapidly. All stars rotate because they form swirling clouds of interstellar matter. As a star collapses, it must rotate faster because it conserves angular momentum. So you guys are still happy with the principle of angular momentum? So best idea to describe angular momentum: if you see an ice skater on an ice skate ring with her arms extended, she will spin slowly, but when she pulls in her arm closer to her body, she spins faster, and that is the conservation of angular momentum. So that means when the star's radius all of a sudden shrinks, it must spin faster. The same principle with the ice skater pulling in her arms. So the smaller body, the faster the spin. That's almost true. So if you think about it, you have the large body. So you can think about the radius of a large body as the ice skater's arms. And now that body is all of a sudden collapsing and shrinking in itself. So the radius is becoming smaller. So you can think about the arms are being pulled closer to the body. So therefore, the smaller body will spin faster. So if the sun collapsed to a radius of 10 kilometers, its rate of rotation would increase from once every 24.5 days to more than 2,000 times a second. You might expect the collapse of a core of a massive star to rotate in a range of 10 to 1,000 times a second. It isn't hard to understand how a neutron star could have a powerful magnetic field. All stars have magnetic fields, and some have fields 1,000 times stronger than the sun's. The field is frozen in the ionized gas of the star, and when it collapses into a neutron star, the field is squeezed down, concentrated, and made as much as 1,000,000,000 times stronger. Theory predicts the properties of neutron stars, but it also predicts that they should be difficult to observe. Neutron stars are very hot, so from your understanding of blackbody radiation, you can predict they will radiate most of their energy in the gamma ray and X-ray part of the spectrum. Radiation that could not be observed in the 1940s and 1950s because astronomers could not yet put telescopes above Earth's atmosphere. Also, the small surface areas of neutron stars mean that they will be very faint. Consequently, astronomers of the mid-20th century were not surprised that none of the newly predicted neutron stars had been found. Neutron stars were, at that point, entirely theoretical objects. Do you all know who this lady is? So you don't know who this is? Would you like me to describe Jocelyn Bell? Okay, so today she is Professor Dame Jocelyn Bell Burnell. So she was knighted in the UK and has the rank of full professor. She is also involved with the University of Cambridge. And if we just remember correctly, yes, she was the first person to discover pulsars. No, she's not related to Alexander Graham Bell. Um, so she discovered the first pulsar. So in 1974, she was recognized by the award for a Nobel Prize. But despite being the first person to discover the pulsar, she was not one of the recipients of the prize. So in November 1967, so just curious, is the highest qualification a professor or a doctor? So speaking about qualifications, the highest qualifications you can receive is a doctorate, so a PhD. And then you have a few academic ranks above it. So the first will be associate professor. So to achieve the rank of associate professor, you need to have a PhD, and then you need to have a certain amount of research that you have done, so a certain amount of research under your belt. And then you can be appointed associate professor. And then if you have done even more research and supervised more students, then you can get the rank of full professor or professor. Yeah, so no one just automatically received the rank of professor. So you first have to finish your PhD. Then you have a certain amount of papers you need to publish to be, yeah, have a certain amount of publications behind your name. You have to have an X amount of students that you have supervised on master's and PhD level. And then you can be considered for the rank of associate professor. And usually when you receive the rank of associate professor, so you will see when in your graduation ceremonies and watching graduation ceremonies, undergrad degrees, the toga that you wear looks the same, and the color of the band across your shoulders corresponds to the faculty you're registered in. And then when you go to honors level, the band across your shoulder is a little bit different and a little bit thicker, but the robe remains the same. On master's level, you get a totally different robe or wear a totally different robe. On doctorate level, you wear a different robe as well. Then when you are appointed as associate professor, you get a different robe as well, and you also need to give a inaugural lecture to the university. So you are inaugurated as an associate professor, and when you achieve the rank of full professor, you get inaugurated as a full professor, and you have to give a inauguration lecture as well. And if you so the only place that can give you the rank of associate professor or professor are research interest institutes such as universities. And if you, for example, leave the university or resign and go to a different place, then you lose the title of professor or associate professor. But so but if you retire while being a associate professor or professor, then you keep the title for the rest of your life. So in November 1967, Jocelyn Bell, a graduate student at Cambridge University in England, found a peculiar pattern in the data from a radio telescope. Unlike other radio signals from celestial bodies, this was a series of regular pulses. Yes, then you're correct. Then you get the title Emeritus Professor. So if you move from one university to the other, then you keep your title. So let me try to. So when you say, for example, when you move over from one university to a different university and you have the rank of professor, then you keep it. But say, for example, when you are a professor in university and you decide you are going to quit and move over to industry, then you lose your title because you're no longer affiliated to a university or research institute, and therefore you're not, you could say, worthy to keep the title of professor. The same thing happens, for example, with the state president. That you guys know, once a president finish their terms, one term or both terms as president, they keep their title for the rest of their life. So for the rest of their life, they will still be addressed as Mr. President or Madam President. But if you are impeached or quit while you were president, then you lose the title as well. So when you have time on free time, go on YouTube, look about interviews of Jocelyn Bell Burnell. So in the 60s, it's not like today. So when we use spectrographs and continuous observation, we didn't save it to hard drives like we have now in computer systems. So you guys know what tape recorders and tape is? So I don't know if this is a bit before your time, but do you guys remember those dot matrix printers? Or a better example will be in movies. When somebody does a polygraph test, you will see that little needle drawing lines on a piece of paper. This is exactly the same thing. So the data we got from telescopes were actually printed on paper and not saved on computers. So all the data processing happening in the early 1950s, 1960s, 1970s had to be done by hand. So what happens is with Jocelyn Bell, she was observing a radio object, and then all of a sudden there were peaks in the data. And then she started measuring the peaks and figured out that these peaks have the same period. So at first she and the leader of a project, Anthony Hewish, thought the signal was interference from earthly sources. But I found it day after day in the same place in the sky. Clearly it was in celestial origin. Another possibility that came from a distant civilization led him to consider naming it LGM for Little Green Men. But within a few weeks, the team found 3 more objects in other parts of the sky pulsing with different periods. The objects were clearly natural, and the term dropped the name LGM in favor of pulsar, a contraction of pulsating star. The pulsing radio source Ballard observed with a radio telescope was the first known pulsar. And interesting enough, the telescope she observed it with was at the Jodrell Bank Observatory in Cambridge, UK. Also, something interesting, you guys are familiar with the SKA project? So the SKA, so MeerKAT will become the SKA. Then the other part of the SKA is built in Australia. And then there are different countries contributing to the SKA project. So currently now there are 22 countries involved with the SKA. So to control all these countries' part in the project, the organization controlling it is called the SKAO, so the Square Kilometre Array Organization. And the SKAO headquarters is situated in Jodrell Bank. As more pulsars were found, astronomers argued over their nature. The period ranged from 0.033 to 0.75 seconds, and each one was nearly as exact as an atomic clock. Are you guys familiar with atomic clocks? Okay, so let me explain. Atomic clocks is boring to look at, but it's probably one of the most coolest things ever. Where I am at Hardrau, we have 3 atomic clocks. So you get a few different models of them. So we have 2 methanol and 1 hydrogen atomic clock. So let's take the methanol, for example. So our atomic clock is a vacuum-sealed chamber with 1 molecule in. So hydrogen was a common atomic clock, and methanol is also another common atomic clock. Another word for these clocks are also masers. So in atomic clock, let's take the methanol one, for example. You pump in a molecule of methanol inside the chamber. You give it a slight electric current. Then it starts oscillating up and down in chamber. So it will hit the bottom of the chamber, then bounce back up to the top of the chamber, bounce back down. And that timing it takes from the top to the bottom of the chamber and the bottom to the top is the most accurate way to keep time. Currently, it's as accurate, so the ones we use is how did I figure out how long 1 second is? That's comes from the Bureau of Standards. I'm not sure about that. But the oscillation in these atomic clocks is 10 to the power minus 18th of a second. Yes, cesium-133 is also used in atomic clocks. Yes, cesium is also one. The hydrogen and methanol clocks is more common in cesium these days. Yes, Mr. Luguio.
Sir, do all atoms oscillate at the same frequency? Because I don't think so. So wouldn't there be?
No, not all atoms oscillate at the same frequency, but you can manipulate them to oscillate at the same frequency.
Oh, so they wouldn't be so you can use two different atoms, but depending on the conditions, you can make them oscillate at the same.
Yes, you can.
Oh, okay. Thank you, sir.
Pleasure. So it was easy to eliminate possibilities. Pulsars could not be ordinary stars. A normal star, even a small white dwarf, is much too big to pulse that fast. Nor could a star with a hot spot on its surface spin fast enough to produce the pulses. Even a small white dwarf would fly apart if it spun 30 times a second. The pulses themselves gave the astronomers another clue. The pulses last only about 0.001 seconds, placing an upper limit on the size of the object producing the pulse. If a white dwarf blinked on and then off in that interval, you will not see a 0.001 second pulse. That's because the point on a white dwarf closest to Earth would be about 6,000 kilometers closer than its center. And light from that spot would arrive 0.02 seconds before the light from the bulk of the white dwarf. As a result, its short blink would be smeared out into a longer pulse. This is an important principle in astronomy. An object cannot change its brightness appreciably in an interval shorter than the time it takes to cross its diameter. If pulses from pulsars are no longer than 0.001 seconds, then an object cannot be larger than 300 kilometers in diameter and could be much smaller. Only a neutron star is small enough to be a pulsar. In fact, a neutron star is so small that it couldn't pulsate slowly enough, but can spin as fast as 1,000 times a second without flying apart. The missing link between pulsars and neutron stars was found in 1968 when astronomers discovered a pulsar at the heart of the Crab Nebula. The Crab Nebula is a supernova remnant, and theory predicts that some supernova leave behind neutron stars. The short pulses and the discovery of the pulsar in the Crab Nebula was strong evidence that pulsars are neutron stars. Now we're going to look at a model of a neutron star. As you have noticed before, scientists often work by building a model of a natural phenomena. Not a physical model made of plastic and glue, but an intellectual conception of how nature works in a specific instance. The astronomer's model may be limited and incomplete, but it helps them recognize the understanding. The modern model of a pulsar has been called a lighthouse model, so notice three important points. So yes, neutron stars are pulsars. You are correct. A pulsar does not pulse, but rather emits beams of radiation that sweeps around the sky as the neutron star rotates. If the beams do not sweep over Earth, the pulses will not be detectable by Earth's radio telescopes. Secondly, the mechanism that produces the beams involves extremely high energies and is not fully understood. Then thirdly, modern space telescopes observing from Earth's atmosphere can image details around young neutron stars and even locate isolated neutron stars whose beams of electromagnetic radiation do not sweep over Earth. So the easiest way to visualize a neutron star is like a lighthouse flashing a beam in the distance, where this beams in a neutron star is now electromagnetic radiation that flashes across Earth while it rotates. But as we learned in astronomy, pulsars can also evolve. So when a pulsar first forms, it is spinning fast, perhaps 100 times a second. The energy it radiates into space comes from its energy of rotation. So as it blasts beams of radiation outward, its rotation slows. The average pulsars are apparently only a few million years old, and the oldest are about 10 million years old. Presumably, older neutron stars rotate too slowly to generate detectable radio beams. You can expect that a young neutron star should emit powerful beams of radiation. The Crab Nebula is an example. Only about 960 years ago, the Crab pulsar is so powerful it emits photons all across the electromagnetic spectrum at radio, infrared, visible, X-ray, and gamma-ray wavelengths. In this image, we can see high-speed images of the Crab Nebula pulsar show it pulsating at visual wavelengths and at X-ray wavelengths. The period pulsation is 33 milliseconds, and each cycle includes 2 pulses as its 2 beams of unequal intensity sweeps over Earth. So here is the main pulse and a secondary pulse, and this is in the visual light. And you can see an X-ray is our main pulse and our secondary pulse. Only the most energetic pulsars produce short wavelength photons and thus pulse at visible wavelengths. The Crab Nebula pulsar is a young and powerful, and it produces visible light pulses. So does another young pulsar called the Vela pulsar, located in the southern hemisphere constellation Vela. So here we can see the Milky Way galaxy radio image. Here we can see the Vela pulsar. Here we can see the Crab pulsar and 2 other pulsars as well. But when we observe pulsars, we can see the pulsars via a radio image, and here we can see a jet leaving it. So that jet is from the pulse. Compared with most pulsars, the Vela pulsar is fast, pulsating about 11 times a second, and like the Crab Nebula pulsar, is located inside a supernova remnant. Its age is estimated a rarely young 20 to 30,000 years. The Fermi Gamma Ray Telescope, Space Telescopes, or Fermi Telescope, has detected a new kind of pulsar that pulses in pure gamma rays. It is not clear how these pulses are produced, but because gamma rays are extremely short wavelength, high energy photons, the producers must involve very high energies. At least one of those gamma ray pulsars is located inside a supernova remnant that is only about 10,000 years old. So something interesting. Are you guys familiar or read up about who the top management of MeerKAT is? So not MeerKAT, so right now all radio astronomy activities in South Africa are governed by SARAL, the South African Radio Astronomy Observatory, and that includes the MeerKAT telescope, the CAT-7 telescope, and the Hartebeesthoek telescope where I am. So for the organization, you need the director of the organization, then you need your different positions, such as the chief principal scientist. So our chief principal scientist is Dr. Fernando Camilo, and his field of expertise is studying pulsars. And MeerKAT till this day has discovered a few more pulsars that wasn't known before. So this is an image of the Fermi Space Telescope. Is everyone still awake? Everyone still following? Awesome. The electromagnetic energy in the beams is just a small part of the energy emitted by a pulsar. So going back an image, this big block, those are the detectors to detect X-rays and gamma rays. So roughly 99.9% of the energy flowing away from a pulsar is carried as a pulsar wind of high-speed atomic particles. This can produce small, high-energy nebula near a young pulsar. So here we can see the effects of pulsar winds can be seen at X-ray wavelengths. This high-energy gas of the winds is sometimes detectable, as is the interaction of the winds with the surrounding gas. Not all pulsars has detectable winds. So here we can see a supernova remnant and a ring of jet around it produced by the pulsar. So here we can see the pulsar, and here we can see the supernova remnant, and this in the blue is the pulsar wind. So here we can see the same, the Vela supernova remnant, and here we can see rings that is produced by the pulsar wind. You might expect to find all pulsars inside supernova remnants, but the statistics must be examined with care. Many supernova remnants probably do contain pulsars, but their beams never sweep over Earth. Also, some pulsars move through space at high velocity quickly, leaving their supernova remnants behind. So in this image, we can see many neutron stars have high velocities through space. Here the neutron star known as RX was photographed on 3 different dates as it rushed past background stars. And like we get binary stars, we get binary pulsars as well. Nearly 2,000 pulsars are known, and some are located in binary systems. These pulsars are of special interest because astronomers can learn more about the neutron star by studying the orbital motions of the binary. Also, in some cases, mass can flow from the companion star onto the neutron star, and that produces energy violence. The first binary pulsar was discovered in 1974 when astronomer Joseph Taylor and Russell Hussell noticed that the pulse period of the pulsar PSR B1913 plus 16 was changing. The period first grew longer and then grew shorter in a cycle that took 7.75 hours. Thinking of the Doppler shift seen in spectroscopic binaries, the radio astronomers realized that the pulsar had to be in a binary system with an orbital period of 7.75 hours. When the orbital motion of the pulsar carries it away from Earth, astronomers see the pulse period string lengthen slightly, a redshift. Then when the pulsar rounds its orbit and approaches Earth, they see the pulse period shorten slightly, so just blue shifted. The resulting graph of radial velocity versus time was then analyzed to find the shape of the pulsar's orbit. The analysis of the PSR pulsar showed that the binary system consisted of 2 neutron stars, one of which is silent, separated by a distance roughly equal to the radius of our Sun. So here we can see is the center of the mass, the pulsar, and here we can see the radial velocity of these binary system. Yes, Mr. Levuyo.
So is it possible for like planets to still orbit around? Because like, okay, I understand that the star like sort of blew up and then it collapsed, but like, so is it possible that planets can still surround the neutron star?
Yes, it can. It completely can. So I pressed now the wrong button. I'm just going to open up the slides again. So yes, it can. So if the planet's orbiting the system is not blown up by the supernova, and if there's still enough mass in the system to keep the binary, to keep the stars around the planets, around the neutron stars, then yes, it can.
And so can the neutron star emit enough energy so that like the the planet itself can be like sort of warm?
Unfortunately not. Usually when a star reaches that point of life, there's not enough surface area to radiate energy from to give enough energy to the planets.
Even if the planet itself moves much closer to the neutron
Yes,
star.
unfortunately not.
Okay, and so you said that some neutron stars are detected while they're moving, right?
Yes. So let me see if I can quickly get an animation to explain this concept. Let me quickly search.
And so I understand that, like, like our sun is also moving in
Yes.
so does that mean, depending on how fast the star moves, like, will the speed in which our sun orbits the center of the galaxy, will that affect it, like anything that happens to the Earth itself?
Not really, but let me show you an animation that will explain this to you. So just give me a moment, I will quickly. Okay, I'm quickly going to share this tab, and this should explain what is going, how everything orbits. So, Chrome tab. So that should give the idea of what's happening in space. So while the planets orbit the sun orbits the center of our own galaxy.
And so that analogy at the end, so when they said something about the vortex, is that where the analogy of Einstein's um, um, example of what gravity is like? For example, it's like planets rolling around into a well, if that makes sense.
Almost, but we will get to that as well.
Okay, thank you, sir.
It's a pleasure. So, how far have we moved? Let me quickly get that information for you. So it takes the sun approximately between 225 and 250 million years to orbit our own galaxy, at the center of our own galaxy. So if we quickly do the calculations, the sun has done about 20 complete loops or orbits around the galaxy, our own galaxy. So since our sun is rotating around the galaxy, what is sun's gravity to pull the sun around the galaxy? And that is what we are building up to, and that is a supermassive black hole. So where is the universe going if that is the case? The universe is expanding in all directions. So yet another surprise was hidden in the motion of PSR pulsar. In 1916, Einstein's general theory of relativity described gravity as a curvature of spacetime. Einstein realized that any rapid change in gravitational field should spread outward at the speed of light as gravitational radiation. Tyler and Hussel were able to show that the orbital period of the binary pulsar is slowly growing shorter because the stars are radiating orbital energy away at exactly the rate expected for gravitational radiation, and so are gradually spiraling toward each other. So normal binary stars are too far apart and orbit too slow to emit significant gravitational radiation. Tyler and Hussel won the Nobel Prize in 1993 for their work confirming general relativity using binary pulsars. In 2016, it was announced that a Laser Interferometer Gravitational Wave Observatory, LIGO, had made the first direct detection of gravitational radiation. So a few comments. So yes, the universe is expanding everywhere. And then, is the sun also being drawn into the inner parts of the galaxy? No, the sun is not being drawn into the inner parts of the galaxy. Can everyone still hear me? So dozens of pulsars has been found orbiting stars of various kinds. By analyzing the Doppler shifts in their pulse periods, astronomers can estimate the masses of the neutron stars. Typical masses are about 1.4 solar masses, as predicted by theory. In 2004, radio astronomers announced the discovery of a double pulsar, two pulsars that orbit each other in only 2.4 hours. One spins 44 times a second, and the other spins once every 2.8 seconds. The system is a pulsar jackpot because the orbits are nearly edge on to Earth, and the powerful magnetic fields and the gas trapped in the fields eclipse each other, giving astronomers an opportunity to study their size and structure. Furthermore, the theory of general relativity predicts that these pulsars are emitting gravitational radiation, so that their separation is decreasing by 7 millimeters per year. The two neutron stars will emerge in about 85 million years, presumably triggering a violent explosion. In the meantime, the steady decrease in orbital period can be measured, giving astronomers another test of general relativity and gravitational radiation. So yes, it's just a single black hole keeping the galaxy together. So basically all galaxies has a supermassive black hole in their cores, but we're going to discuss that in later chapters as well when we're going to start discussing a galaxy as a whole. The gravitational fields of neutron stars are so strong they can be sites of titanic violence. An astronaut stepping onto the surface of a neutron star would be instantly smooshed into a layer of only 1 atom thick. If you dropped an apple onto the surface of a neutron star from a large distance, it would hit with an impact equivalent to a megaton nuclear bomb. In general, a particle falling from a large distance to the surface of a neutron star will release energy equivalent to 0.2 mc squared, where m is the particle's mass at rest and c is the speed of light. So here we can see the binary pulsars. So in image A, we can see sometimes X-ray pulses from Hercules X1 are on, and sometimes they are off. A graph of X-ray intensity versus time looks like the light curve of an eclipsing binary. Then in image B, in Hercules X1, matter flows from a star onto an accretion disk around a neutron star, producing X-rays, which heat the near side of the star to 20,000 Kelvin, compared with only 7,000 Kelvin on the far side. X-rays turn off from Earth's point of view when the neutron star is eclipsed behind the star. Here in image A, we can see at visible wavelengths, the center of star cluster NGC 6624 is crowded with stars. And in image B, in ultraviolet one object stands out, an X-ray source consisting of a neutron star orbiting a white dwarf. Then in image C, an artist's representation shows matter flowing from the white dwarf onto an accretion disk around a neutron star. But these pulsars can become really fast. So to your knowledge of pulsars, suggesting that newborn pulsars should blink rapidly and old pulsars should blink slowly. In fact, the handful that blink the fastest may be quite old. The currently fastest known pulsars catalogued as PSR J1 and that number. It pulses 716 times a second and is slowing down only slightly. We call that millisecond pulsars. A number of other very fast pulsars has been found. They are generally known as millisecond pulsars because their pulse period and therefore their periods of rotation are around a millisecond. So how are they named, sir? So usually there's different naming conventions for different objects. So it usually is the PSR or the NGC is the classification it falls under. And then like you have an ID number, a person, the rest of the number is just a unique identifier. And then usually a name is given to it afterwards, such as the Vela pulsar or the Crab pulsar to make it easier to describe. This rapid rotation produces some fascinating physics. If a neutron star 10 km in radius spins 760 times per second, then its equator must be traveling at almost a sixth of the speed of light. So here we can see the Black Widow pulsar and its companion star are moving rapidly through space, creating a shock wave like the bow wave of a speedboat. The shock wave confines high energy particles shaped by the pulsar into an elongated cocoon. And now, pulsar planets. Becoming a pulsar period is so precise, astronomers can detect tiny variations by comparing their observations with atomic clocks. When astronomers check pulsar, so PSR B1257 plus 12, they found variations in a period of pulsation much like those caused by the orbital motion of binary pulsars. However, in the case of PSR B1257 plus 12, the variations were much smaller. When they were interpreted as Doppler shifts, it became evident that the pulsar was being orbited by at least two objects with planet-like masses of 4.1 and 3.8 Earth masses. The gravitational tugs of these planets make the pulsar wobble about the center of mass of the system by no more than 800 kilometers, producing the observed tiny changes in period. So here we can see in image A, the data points of this graph represent observations showing the period of pulsar PSR plus 12 varies from its average value by just 10 trillionth of a second. The blue line indicates the variation that would be produced by the best fit model for the two largest of the three planets orbiting the pulsar. In image B, as the planets orbit a pulsar, they cause it to wobble by less than 800 kilometers, a distance that is invisibly small in this diagram. The outermost planets orbit at about 0.46 AU from a pulsar, farther than Mercury but closer than Venus from the Sun. And now we get to the second part of this lecture, and what is black holes? Do you all recognize this image? Yes, that's the first image of a black hole. So yes, M87. So I know about 3 weeks back I showed a cool talk in a presentation in a conference I was attending about how the first image of black hole was captured. So I'm going to give you guys two options. We can continue on with the lecture, then I show you the video, or I show you the video and then we continue on with the lecture, if you guys want to see it. Guys want to watch this? I know some of you might have seen a video when I played it. By the way, there's not many people in the class. I think it was about 20 people in the class, but I think this will be good for you. So this is a conference I attended 3 weeks ago. So I'm part of the group called CASPER. It stands for the Collaboration of Astronomy, Signal Processing, and Electronics Research. So the group aims to find better technology, software libraries, software, and techniques to study celestial objects. So this is one of the persons that was involved with the Event Horizon Telescope and was part of the process of imaging the black holes. So let me show you her talk from the conference.
Have Sarah Ision to talk about, she's an expert on black holes, and in particular on the black hole at the center of our galaxy, Sagittarius Star, and she and her collaborators use CASPER instrumentation to make the very first images of black holes, and I think she's going to tell us all about that. Thank you, Sarah.
Thank you very much. So it seems screen sharing is not possible. Could that be enabled?
Hey Sarah, try again.
Okay, there we go. Thank you. All right, thank you very much for inviting me to talk about our project. It's really exciting. I'll try to spend a lot of time.
Same general time as this work.
Gigahertz, which is the frequency.
Extremely fortunate to have Sarah Ision to talk about, she's an expert on black holes, and in particular on the black hole at the center of our galaxy, Sagittarius Star, and she and her collaborators use CASPER instrumentation to make the very first images of black holes, and I think she's going to tell us all about that. Thank you, Sarah.
Thank you very much. So it seems screen sharing is not possible. Could that be enabled?
Hey Sarah, try again.
Okay, there we go. Thank you. All right, thank you very much for inviting me to talk about our project. It's really exciting. I'll try to spend a lot of time on the instrument and then give some context on science. Of course, I'm a member of the EHT, so everything I say is on behalf of our amazing collaboration, which is very diverse, and we have, telescope staff and engineers and scientists working on lots of different aspects of the project. So first off, why do we care about imaging a black hole? Why is this important? So first of all, black holes are mathematical occurrences of the theory of general relativity, and they also exist as astrophysical objects, which is quite amazing. They are very extreme environments where time and space come to a halt, and physics is at its most extreme. On top of that, we believe that supermassive black holes reside in the centers of most large galaxies, and they eject these streams of matter, which we call jets. These jets pierce entire galaxies into galaxy neighborhoods, sometimes thousands of light years in length, and they're the most energetic and powerful process in our universe. But we don't really know why that happens. We think, the central engine is the supermassive black hole. We think magnetic field and pressure and gas forces play a role, but we don't really understand what is the mechanism that causes these. So in order to understand, where this comes from, we need to look at the central engine, which is a supermassive black hole. We have two supermassive black holes big enough to image from Earth, the one at the center of our galaxy, Sagittarius A star, and the one in the galaxy M87. M87 you can see in the corner here. It is over here. Has a well-known jet. It is actually the first astrophysical jet ever observed by humanity. It was observed in 1918 with the Lowell Observatory in optical, and they saw this stream of matter coming from this tiny point, which is the galaxy itself. And in fact, what powers it is the supermassive black hole. So if we look at the night sky in the Virgo constellation, there is a galaxy called Virgo A, or M87, 55 million light years away from us. Because there is a lot of gas and dust between us and the center of the galaxy, we need to observe in radio waves. Although this stream of matter, this stream of plasma is visible in the optical and radio, only radio can peer all the way down to the center because it's not absorbed by gas and dust. So if we use radio waves at higher and higher frequency with larger and larger instruments to increase our resolution, we can zoom down, follow the stream of matter all the way down to its core, which is where we observe with the EHT, the black hole M87. And with the EHT, we observe at a frequency of 230 gigahertz, which is the frequency high enough so that we can peer through all the way down to the black hole. And also, it just happens to be the frequency that gives us a resolution that lets us image the shadow. Now, in order to piece together a synthesized Earth-sized instrument, we use a technique called very long baseline interferometry. So I'll explain a little bit how this works. So say we have a source very far away, so that if we are in the far field regime of radiation, because it's far away, the waves that arrive on Earth are plane waves. Because of the Earth's geometry or curvature, there is a time delay between the arrival of a specific wave at each telescope. Now, the distances between telescopes tell us information about the image. Telescopes close together tell us about information on large scales because they see a lot of signal in common. And telescopes further apart see smaller signal in common, so they see a small scale structure in the image. So by combining many different telescopes at different locations on Earth and at different distances from each other, we can piece together different directions, orientations, and scales in our image and combine them. So this time difference is, however, quite important because we want to be able to correlate the signal received at each telescope. So in order to see what signal is in common, we need to time tag our data. And we do this using atomic clocks called masers. They're hydrogen maser transitions that time tag our data with very precise time. And these clocks are so precise, they lose about a second every 100 million years. Now, once our data packets are time tagged, they're recorded onto hard disk. They essentially freeze the light received at each telescope and record them and then combine them at a later time where we can then align the signals and reconstruct an image. So the EHT project is a 10-year project. The first multi-baseline, multi-telescope observation was done in 2007. Then as we expanded the array, we've added more and more telescopes, and some telescopes got decommissioned, so we lost them as well. And then finally, in 2017, we made our famous observations. In 2017, we had 8 telescopes at 6 different locations, 6 single dishes, and 2 phased arrays. Now you'll notice all of these telescopes look very different from each other. This is because we did not build them. They were built for completely different science, so self-standing science. And we just happened to borrow them because they can observe at 230 gigahertz, the frequency at which we need to get to M87, and they are at high enough and dry enough places, and at the right places where we can reconstruct an image from different scales. So high and dry places some of the most dry deserts on the planet, is extremely crucial for our observations. Because we're observing at such a high frequency, we are very susceptible to water vapor and turbulence in the atmosphere between us and space. And the Earth's atmosphere scrambles our signal and absorbs it because of the water vapor. So we really need to pick the right sites that maximize our signal. And our signal is very weak. So our black hole image has a total flux density of about 0.6 Jansky, so almost half a Jansky. And if you take into account all of the radio observations made in the history of humanity, it is less energy contained in that than a single snowflake dropping to the ground. So we're looking at really, really small signal, and it is really crucial that we build sensitivity. So building sensitivity with the EHT means increasing the recording bandwidth and frequency bandwidths. So across many years of our radio observations, we have different systems. The ones that matter the most is our current system here with the Roach 2 digital backend and the Mark 6 recorders. So our 2017 observations recorded at 32 gigabits per second. So this is following, the law of the doubling bandwidth, which is quite amazing that we're able to see this biannual doubling with our own observations and equipment. So we observed at 32 gigabits per second with 2 polarizations and 2 gigahertz basebands. So 2 polarizations because we want to make polarization maps of the magnetic fields around the black hole, and I'll show a little bit of that later. Since then, we are now at 64 gigabits per second, so we've doubled our frequency bandwidth as well to make more polarization and frequency studies. So the signal we receive at the telescope is, of course, an analog signal, and it's 230 gigahertz, so it's very high frequency. We down convert it to a 2 gigahertz baseband with block down converters, and then we digitize it with our Roach 2 digital backends with 2-bit sampling. And then they're recorded onto our Mark 6 recorders. This is one example of one Mark 6 unit. There's 4 boxes here, which we call modules. These Mark 6s, one records at 16 gigabits per second. We need 4 Mark 6 recorders to record at 32 gigabits per second with 2 polarizations. So there's 4 modules per Mark 6, and each Mark 6 contains about, each module contains 8 helium-filled hard drives, which you can see stacked here. All our Mark 6 recorders are equipped with custom cooling for high altitude use. All our equipment needs to be heavily tested at high altitude in these kind of pressure chambers because at sites we're at least 10,000 feet above ground, sometimes 15, 16,000 feet. So we definitely do not want equipment to overheat. Also, including our equipment is not well exercised. We only observe about 2 to 3 times a year, including our dress rehearsals where we practice observing. So we really need to make sure all our equipment can easily start up and not run into too many issues when we do observe. So this is what one full backend looks like. This is from Spain. And you can see here are our 4 Mark 6 recorders. We have our digital backends here, our digitizers, our down converters. And for the total of our 2017 campaign, we used 92 individual modules for 736 hard drives. In total, we recorded about 3.5 petabytes of data across our 5 triggered days. So we observed for a 12-day window during our EHT campaign, 5 days to trigger for observations, and we need to keep a very close eye on the weather. As I mentioned, we have stations at very high and dry places, but that doesn't guarantee best weather all the time, especially in April, when we observe, it's kind of marginal weather everywhere. So we need to look for these pockets of good weather for half the Earth, which is really difficult, and a really difficult task to coordinate. We were really lucky because in 2017 we had probably the best weather we've ever had, and I don't think we'll ever have this kind of weather again. So we keep a very close eye on current and forecasted weather and telescope operations to figure out when to trigger. So here are some nice pictures from our 2017 observations. On top of having operational local staff at the telescopes, we also send our own EHT members to the telescope. Here are some pictures of our EHT members with local staff. And they act as our local experts for backend equipment and for the telescope. Then once we record the data, they get shipped to our correlation facilities, these two places, MIT Stack Observatory and the Max Planck Institute for Radio Astronomy. Each facility correlates about half of the data. So at correlation, we combine the signals from each telescope, we align them, we throw away all the noise that is telescope specific, only to keep the signal seen in common between pairs of telescopes. And it takes into account the Earth's curvature and these timing effects that we measure from our equipment. One thing that it doesn't take into account is, again, the atmosphere. And atmospheric effects, because we have this jitter in our phases in the data, it prevents long averaging. So if we average turbulent data, we end up destroying our signal instead of piling up and building signal to noise. So we need further data calibration. The advantage, though, is that we record at very high bandwidth. And so we do have the signal to noise to actually track atmospheric changes in the data. So from that, we can refine corrections from correlation and remove the effects of the atmosphere. So here's an example. So this is real data from EHC. So in yellow, you can see amplitudes, and in blue, phases from 3 baselines or 3 pairs of telescopes. Now, because we expect the phases from the source to vary very slowly, these few second phases, so this is over time over 400 seconds, these few second phases changes are entirely due to the local atmosphere. And so if we look at these 3 baselines, these are pairs of total of 3 stations, we can actually triangulate which changes actually happen at each station. And because ALMA is the most powerful radio astronomy observatory in the world, and it brings amazing sensitivity, the baselines to ALMA allow us to have amazing signal to noise to actually track atmospheric phases on second scale and actually remove them. So once we remove them, this is what the phases look like. So now if we average down over our entire scan over a few minutes, we build sensitivity. We don't destroy signal anymore. And this is all real data. This is really what it looks like. And it's really amazing because of our high recording bandwidth, we're able to build enough sensitivity to track and remove effects of the atmosphere and really build our data, build our signal to noise, and build confidence in our data. Now, of course, understanding the data is one step, but understanding telescopes is another. We need to understand how our telescopes work, what are their sensitivities, so that our detections, which are now a signal to noise, go into a flux density scale. We need them in Jansky so that we can make an intensity map. So in order to do that, we need to take into account, again, the sensitivity from the atmosphere, the size of the dish, different surface, elevation effects, signal chain, noise level, and also polarization leakage. Now, I mentioned that our total intensity image was about half a Jansky. The polarization signal is even less than that, way less than that. And so polarization leakage is very important to remove because it creates false signal in polarization, and we really need to remove it very accurately in order to make polarization maps. But there's a trick to it. So we decouple leakage and pure signal using the Earth's rotation. So because we observe for such a long time, one observing track is about 8 to 9 hours, each telescope sees the source move in an arc on the sky. So the signal from the source, the real polarization signal, is expected to move over time, but the instrumental contribution from the telescope stays put on the ground. So if we combine each arc from the telescopes, we can separate those contributions. So our entire data path from the raw signals, which is 3.5 petabytes, all the way down to an image, which just can be sent on your phone, is about 12 orders of magnitude in data reduction. And the most powerful data reduction actually happens at the calibration stage. So now that we have our final data, we can start imaging. And we use, again, the Earth's rotation with the technique called aperture synthesis. So because our telescopes are at set location on Earth, as the Earth rotates, we're sampling different parts of our image. So the Earth's rotation helps us build our virtual mirror, which you can see here. So our coverage is in Fourier space. So we're sampling different frequencies in our image. So as M87 becomes visible, we get different pairs of telescopes that give us different tracks on our coverage. And as we pile these data in time and in space, we can see how our image improves. So you can see here how as we build up our data and our coverage, the image takes shape. So we imaged M87 with 3 different softwares. This one was a traditional technique for historical VLBI. These 2 were designed for EHT specific issues, dealing with systematics from our high sensitivity and our sparse coverage that we have. And all 3 gave very good answers. We tested all of these softwares against synthetic data where we knew the ground truth to make sure that we picked the right optimal parameters for our software, and this is the final result. So these are the 3 software images for April 11 observation, and in fact the famous image I'm sure you've seen of the black hole is simply the average of these 3. So that is the first image of a black hole. But during our 2017 campaign, we triggered 5 observing days. 4 of them had M87, so we have 4 individual observations of this ring. This one was April 11. And here are the other 3. So as you can see, over our 4 days, we don't see significant changes. Every single day gives us a ring of the same size, right on the bottom with a dark spot in the center where the black hole shadow is. In polarization, which we just released a couple of months ago, we get these beautiful images. So on top of our total intensity ring, we added the information from polarized light. You can see that polarized light only lights up the southwest part of the ring and gives us this kind of spiral structure in the polarization angles. So we get a spiral polarization structure across our 4 days, and it looks pretty similar across the days as well. I'll explain everything that we learned from this. First, we measured the size of our black hole, which was 42 microseconds on the sky, which is because we know the distance of the black hole, we were able to measure the mass, which is 6.5 billion solar masses. M87 is one of the largest and most massive black holes in our known universe. I really love this comic because it actually shows us the scale of this image. Although it's 42 microseconds, it's the size of seeing an orange on the surface of the moon with your naked eye. It is actually bigger than our solar system. So you can see the sun at the center, Pluto, the orbit of Pluto around, and Voyager 1, which is the furthest human-made object that we've sent out, just at the edge of the shadow. Now, the next step is to understand what exactly we're looking at. So we've imaged it. We know it's a ring. We know it has a shadow. What does it tell us about the physics? What are we learning? So in order to do that, we simulate a black hole and its environment. So we use fancy simulations that take into account the space-time around the black hole with general relativity and the physics around it. So we have matter orbiting, falling into a black hole, which is called the accretion disk, and it also spews out these jets of plasma, and then these disks and jets are also threaded with magnetic fields, which help push in and out material, and there's a black hole at the center. And then because of the very hot gas temperature, the gas is not atoms, it's ions and electrons. And so because we have electrons in magnetic fields, if we have very fast moving electrons spiraling around magnetic field lines, they emit synchrotron radiation that is polarized, and that is the emitted light that we observe with the EHT. So from different types of physics that we try to understand, we made a simulation library. So this is our total intensity simulation library to try to understand the signatures of our ring. There are lots of different ones here that have different gas properties, magnetic field properties, but they all have something very clearly in common. They all have a dark patch at the center and a bright ring around it. So why is that? Why do they all show the same thing? It's because this signature in our main image is a direct effect of gravitational lensing. Because we have such a strong pull from the gravity of the black hole, we have light rays from around the black hole that get bent by the gravity of the black hole. And as seen from a distant observer, if you have a lot of light rays, which is the case with the gas around the black hole, as a distant observer, you will see this kind of puffed up shadow surrounded by a ring of light, and that's exactly what we observe. Now you'll also notice that our ring of light is not smoothly uniform. It has a part that is brighter on the bottom. The reason of that is because of the inclination we're looking at. We're seeing a full ring. We're looking almost straight down the barrel of the black hole. And one side is brighter than the other because of Doppler boosting. So the side that is brighter is coming towards us, and the fainter side is going away from us. So another thing we learned from our simulations is also that the gas rotation around the black hole orbits clockwise, and that the spin of the black hole is pointing into the board, into the screen. Then we also looked at polarization simulations. So we have our polarization images. We want to understand what does the magnetic field look like, and whether they actually play a role in launching this famous jet that we see in M87. So we made polarization simulations, which you can see on the left with perfect resolution, and on the right we would see with the EHT. And we compared these polarization maps. So what it teaches us is that if you have a black hole with an accretion disk with threaded magnetic fields, if you have weak magnetic fields, they would kind of look like concentric circles, the field lines. And then the synchrotron radiation that would come from these field lines would look like spokes on a wheel as seen from Earth. So we'd make polarization maps that would look like, that stick out like this, just like the animation. Now, if you have a very strong magnetic field, you will get the opposite effect. You will get spokes on a wheel, magnetic field lines, and then the synchrotron radiation would look like concentric circles as seen from Earth. So this is what our image would look like. But as you remember, our polarization image looks like a spiral, right? And so it means it's kind of in between weak and strong. So if we have a spiral structure of the magnetic field, the synchrotron radiation that we see from the black hole is also a spiral. And so we learned from this that the magnetic field strength around the black hole is about 4 to 30 Gauss, and it has a spiral structure that has a vertical component. The interesting thing about the vertical component is that it means it's able to push gas out, which means that it could be the cause and the direct link between the black hole magnetic field and the jet launching. So that is where we stand now with EH2 results. So what's next for us? We've added new stations since then. We just observed in 2021 with the added Greenland telescope, Tiktik telescope, and Noema array. We're hoping to add a telescope in Africa, but we're thinking about really long term as well, which is the next generation EH2. So with the next generation EH2, we'd like to have, because now we have the sensitivity from our large dishes, like ALMA and like Noema. So we'd like to put small dishes at lots and lots of different places on Earth to fill our coverage. So we're no longer sensitivity limited. And what's really cool is that say you have a simulation here of a black hole and its jet. What we would see with 2017 is just the dominating ring that we see in our images. But we know this jet exists, so we don't yet have the sensitivity and coverage to be able to image it. But with NGHT, we'd be able to image images and link directly the ring to the jet emission from the black hole. And this will really help us understand how the jet behaves and how it connects to the black hole. And we want to extend to space. We'd like to have longer baselines, so no longer limited by the size of the Earth. We'd like to have faster orbiting in low Earth orbit to fill our coverage and go to higher frequencies even. If we have an entirely space-based array, we're no longer limited by the Earth's atmosphere, so we can go to 1 terahertz. But next generation EHT means next generation challenges. This is my final slide. Just to think about where we're going, because we're adding so many more telescopes, we need to look at our monitoring and control development. We can't just keep sending telescope experts to sites, especially if we want to observe more often. We're going to have a lot of data, so we want to expand from our 64 gigabits per second to 256 gigabits per second. We need to think about data storage and real-time correlation. For ground-based array antenna design, we need to look at smaller dishes, which should be sufficient given its current sensitivity. For a space-based array, we're looking at whether we have a single orbiter with our ground array, which allows for quick filling, or an entirely multiple orbiter system, which allows for very slow filling but very sharp images. Then we want to build sensitivity in space. If we want a wide bandwidth and large data rates, how do we get the data down? We can't just keep hard drives there, and we can't send an airplane to get it. So we need to think about how to downlink this kind of data. And also timing in space. So our major clocks that we have at the site are the size of a mini fridge, and we can't really afford to put a mini fridge into space. So we need to think about compact solution for timing, which is really crucial for our signal for VLBI. So I'll stop here. Thank you very much, and I'll take questions.
Thanks, Sarah. That was great. Andre Goons.
Okay, so I know that was a little bit information overload, but I hope this painted a clear image of the black hole. So I saw here, why is helium drives preferred? So helium drives is preferred because you get a little bit longer lifetime out of them, and the data accumulate data error rate is much less. So because a helium-4 drive roughly takes 20% less energy to work, you get much more spin cycles out of it. So that means your disk failure will be a lot less. So just more reliable to use on telescopes. So I see we're a bit over time. So tomorrow night we will finish our section on black holes. So you guys are more than welcome to log off, and I will see you all tomorrow evening. If you have more questions, I will be active for another minute or two. Yes, Mr. Bonolo.
Can I ask one question about black holes?
Yes.
Why does it seem that everything like particles rotate around black holes instead of just going directly to the center, since it has immense gravity? For example, on Earth, if something is in the sky, it goes directly to the center. Why isn't it the same case with black holes?
Okay, so it's the same principle as Earth orbiting around the sun. So we are far enough away from the sun that Earth and the other planets are in stable orbits around the sun. So if there's a certain point around an object, it's called an event horizon. If you are on the event horizon, so let me get the whiteboard, that's going to be easier to explain. So if this is the object, such as, for example, the sun or the black hole, then there's an area around it. This area, let's abbreviate it, called the event horizon. So if we have a different object that's outside of the event horizon, that object can be in a stable orbit around the event horizon. But if you're on the event horizon, then you're going to start being sucked into the object.
Okay,
So
but then the way you're setting the relativity is it won't directly go to the center.
No, it won't go directly to the center. So for example, if we do the same explanation with the sun, Earth is in a stable orbit. So let's draw this again. So let's clear this. So here is the sun. Here is Mercury orbiting it, Venus, Earth, Mars, and we can continue on. So here are our different planets. But there's a point around the sun. And if we reach that point, then we will be sucked into the sun.
Okay.
And the same principle works with a black hole.
Okay.
I hope this
Okay,
answers
yeah.
the question.
It helps. Thank you.
It's a pleasure. So awesome. Have a great evening, guys, and I will see you all tomorrow evening. Thank you for informing me. Just watch the recording when you have time for the lecture. Awesome, guys. Have a great evening, and I will see you all tomorrow.